All right, so 11.2 is on what we call series. Okay, a series is when you add up all the numbers in a sequence. Today we're going to focus on a finite series. Tomorrow, an infinite series. So in the last section, that's the notation that we would use to represent a sequence. Lowercase letter for the name of the sequence, and then a subscript for whatever term that we want to find. Right. Let's list out some of the terms in that sequence. Okay. So let's write down the position and then the term. Okay. Maybe just the first five, six terms. If you plug in, and I want to write it this way. If you plug in 1 for n, what do you get inside the parentheses? That's all I want to know.
1.
Yeah, you get 1 and it's squared. Okay, let's just leave it as 1 squared. What if you plug in 2? What do you get inside the parentheses?
3.
Yeah, you get 3, and then it's squared. What if you plug in 3?
5 squared.
5 squared. And if you plug in 4?
7 squared.
7 squared. So what's happening here is the reason I didn't square them is because you can see the pattern easier. It's odd numbers squared. That's the pattern of the terms. 1 squared, 3 squared, 5 squared, 7 squared, 9 squared, and so on. Now, if we wrote these out, that's 1. What's 3 squared? 9. 5 squared? And 7 squared?
49.
49. Those are the terms. Okay, but I wanted you to see the pattern. So now what we're going to look at is what are called partial sums. When you use a capital S and then a lowercase, like a subscript next to the S, that means to add up the first n terms in your pattern. Okay? So for example, if I wanted to know what S sub 1 is, S sub 1 means to look at these numbers and add up that many of them. Okay, so you're adding up the first term, which is really just the first term. Okay. S sub 2 means to take the first 2 terms and add them up. Okay. S sub 3 means to take the first 3 terms and add them up. And then S sub n would mean to take the first n terms and add them up. Okay, what's n? We don't know, but you're adding up n terms in this case. To represent adding up n terms, because I don't know how many there are, I usually show like the first one, the second one, sometimes the third one, and then I put a ... because I don't know how many more there are. But I know this is the last one. Okay? So let's write these out. Let's actually do the numbers. Okay, we'll do up to S4. Okay, so what does S1 come out to if you do it out?
1.
1. How about S2?
10.
10. How about S3?
35.
So 25 plus 10 is 35. And then let's say we did one more. We did S4. Well, it would be 35 plus what would the next term be?
49.
49. What's 49 plus 35?
84.
Let's see, 49, 79, yeah, 84. Okay, now what I want you to do is look at these numbers. 1, 10, 35, 84. This is another pattern of numbers now. What this pattern of numbers represents is the sums of the first n terms. So if we could start predicting what's going to happen in this pattern, then we could add up as many terms as we want without doing it by hand. Like let's say we wanted to know S sub 200. Well, I don't want to list out all 200 terms and then start adding them up. Okay, that's going to take too long. I would rather figure out a formula with the numbers I already have to figure out what the first 200 would add up to. Right? And that's what we're going to try to do. All right. Any questions on what this notation means? Okay. So each one of those things that we wrote down, S1, S2, S3, S4, they are what we call a finite, because it only had a certain amount of terms in it. It didn't go on forever. It's called a finite series. It's called a finite series. And that's one of the two types of series that we're going to look at. Finite, and the other one is infinite. So suppose that you had some sequence. Okay, in order to have something to add up, you got to start with a sequence. You got to know what your terms are. Once you have those, then you can try to start adding them up and see what you get. So let's say we had a sequence called A. Each one of these things that I wrote down here represents a partial sum. This represents the sum of the first how many terms? Yep, just the first term. That's why when you add up the first n terms, if you're only adding up one, you just get the first term. What does this represent adding up? Yep.
Two terms would be like A sub 1 plus A sub 2.
Right, it represents adding up the first two. S sub 3, you're adding up the first 3. S sub n, you're adding up the first n. Right? So this is called the first partial sum, second partial sum, third partial sum. This is the nth partial sum. And that's what we want a formula for. If we can figure it out, what would be the formula for the nth partial sum? Depending on the numbers, we can get formulas for the nth partial sum. We'll look at certain kinds of problems that the formulas are already well known. Okay, so it's going to be pretty straightforward to figure out. So writing out, like if I wanted to represent writing out the sum of the first 200 numbers, and I actually wanted to express that entire idea, that's a lot of writing. You'd have to write 200 numbers with 199 plus signs. So if I wanted to represent adding up a lot of numbers, but I don't want to write that all out, I can use a compact notation called sigma notation. Has anyone heard of sigma notation before? If you're not too sure, it involves that letter. What's that?
All the freshmen say the word sigma everywhere.
Oh.
So
that's the Greek letter sigma. It's a capital sigma. There's also lowercase, but we're doing it's a capital. And the way that notation works is it has three things on it. You have something on the bottom. Think of this number on the bottom as a starting value. You're going to have a number on the top, which is a stop value. And then you're going to have a formula on the side, which is the formula that's generating all the things you're adding up. So let's say I wanted to represent adding up the first 10 integers. Well, the formula for integer is very, very simple. Let's say we start at 1, and I said the first 10, so I'm going to stop at 10. And then, let me just make sure, I just want to check one thing real quick. Okay, I'm going to use the letter K. So the way this works is, you take this number, you plug it into the formula, and you write down your answer. And then you put a plus sign. Then you make this number go up by 1. So the next number you'd plug in is 2. Plug 2 into your formula, write it down, put a plus sign. You keep doing that until this number reaches 10. So the very last number, second to last number, you do 9, plug in 9. And then the very last number, you do 10, plug that in. And if you went up one more, you'd be at 11, but now you're above the stop value. So this notation right here represents 1 plus 2 plus 3 plus 4 plus 5 plus 6, 7, 8, 9 plus 10. That's what it represents.
Is it kind of like using like f of x, but like just plugging in the different x's?
Yeah, this will be some kind of formula over here. It could be more complicated than just a k. It could be like 2k plus 3. But yeah, there'll always be a formula here. This is the number you're going to start plugging into the formula, and that's the last number you're going to plug in. Generally, it does start with a 1, but they don't have to. They could start with a 0. I've seen that. But 1 is usually pretty common.
So when it says end, that means it's like continuous.
No, this is that's a value that would stop somewhere. It would have an infinity symbol on the top if it went forever.
Okay.
So n means that it does stop. We don't know where it stops, but we know it would stop somewhere. Okay? If you put the actual value for n, then you know this one stops at 10. Right? So unless you see an infinity symbol on the top, it does stop somewhere. Again, you might not know where, but it does stop. So the way that this is pronounced is the sum from k equals 1 to n of, and then you read your formula. That's how you read it. The sum from k equals 1 to n of, and then this is the formula for the sequence. So this is the formula we figured out yesterday. I think I already told you that. K, maybe I didn't tell you that. The number at the bottom, that's called the index. It's like the variable. And that has to be an integer, because this represents a position in the sequence. So it's to calculate the position, it's to calculate the term in a position that you're adding up. So you'd never let this be like 1.6. There's no such thing as a 1.6 term. Okay. All right, so if I wanted to take this and actually write it out the long way, here's the formula. What's the first value they're telling us to plug in for k? 1. What's 2 times 1 plus 3? 5. What's the next value we plug in for k? 2. And that would give me 7. Next value? 3. And that gives me 9. Okay, next value? And that gives me 11. Next value? 5. And that gives me 13. What's the next value?
We stop there.
We're done. We don't go past 5. So this in black is a short way of writing what's in red right now.
After you just add up all in red, or is that just...
Yep, if they wanted to know the actual answer to that, you would have to add all those up. Yep.
So is that how you just gonna write the answer if they don't ask you?
Generally, we're going to be writing, you'll see what we're going to do. We're going to usually have like a formula. Yeah. Okay. In general, they're not going to just tell you to add up 5 numbers. I'm just kind of showing you a real concrete example that has a definite stopping point that you know. All right, so the difference between those two things that I just wrote on the board, on the left side, this is sigma notation. On the right, that's called expanded notation. Okay, and by the end of this, you should be pretty comfortable going either way. Right? Whether I give you something in sigma and I ask you to expand it, or take something that's expanded and write it in sigma notation. Writing it back in sigma notation, you've got to work backwards to figure out your formula. All right, so that's where now you want to think of these numbers think of them as like a sequence, 5, 7, 9, 11, 13. And you've got to figure out the formula to get 5, 7, 9, 11, and 13. And the formula would be 2k plus 3. But you'd have to figure that out. And that's what we learned yesterday. Right. So any question between sigma notation and expanded notation? If you don't know where something stops and you have to go to the nth term, just tell me the first term, the second term. If you want to do the third term, that's fine. But then you can just put ... and plug in the last term. So let's try that on this one. Okay. Is this an infinite sum or finite?
Finite.
Yeah, it is finite. We don't know where it ends, but it ends somewhere. It ends at n. That's where it ends. What's the number for n? I don't know. Okay, so it says to expand the sum. What's the first value you plug in for k? 1. And in the parentheses, what do you get when you plug in 1?
Well, just the parentheses.
Mhm.
5.
Yep.
5 squared.
So 5 squared. You could write 25. I'm just going to write 5 squared. So 5 squared. Let's do the next one. What's the next k value?
7 squared? Or 2?
So the next k value is 2, which gives you 7 squared. All right, let's do one more.
9 squared.
So we plug in 3, and we get 9 squared. And now there's a bunch more that we don't know. But what's the last thing we're going to plug in for k?
2n plus 3 squared.
So what did you plug in for k in that case? N. That's the last number that you plug in. 2n plus 3 squared. And that's how you write out something expanded when you don't know what the last term is, but there is a last term somewhere. Any question on that? Okay. So what we want to do is look at some properties of summations, because this is a great notation for writing something in a compact way, but it doesn't actually help you to do anything fast. Like if I wanted to know in this sequence, if I add up the first 700 terms, what does it add up to? Well, I have a quick way of expressing the idea of adding up the 700 terms. I would just do this. But that's just the idea. It doesn't actually tell me the answer, right? All you know is I want to add up the first 700 terms. So we want to start to get to a quick way of evaluating this and getting the answer. 2,437,000, whatever it adds up to. All right, so for that, we're going to look at some properties of summations. These properties are basically going to allow us to combine and split summations and simplify them. Okay, so here's our first property. And I'll demonstrate this first property with actual numbers. But the idea is, if you have two different sequences, and you want to add the two sequences together, you can do it two different ways. You can either add all the numbers in the first sequence together, add all the numbers in the second sequence together, and then take those two answers you got and add them together. Or you can add the sequences together first, term by term. Add the first term to the first term, the second term to the second term, the third term to the third term, the fourth to the fourth, and then add all those up. Right? And it comes out exactly the same. All right, so let me show you. Let's pick a very short sequence. Let's let a sub k be the sequence 1, 3, 5. Okay, b sub k is 2, 4, 6. So let's add these up the way it is on the right. So a sub k plus b sub k. We're going to do what's in the parentheses first. To do that, you're going to take the number in A, the number in B, and add them up position by position. So what would be the first term in the sum of these two sequences? 3. Second term? 7. And the third term? 11. That's the sequence A sub k plus B sub k. So inside here is 3, 7, 11. Now, take the sum of what you just did. So now let's do the sum of A sub k plus B sub k. What's 3 plus 7 plus 11?
21.
21. So that's the sum of the two sequences, and that's the sum of 3, 7, and 11. Okay, any question on doing it the first way? Okay, now the second way. First, we're going to do that. Add up everything in sequence A sub k. What's 1 plus 3 plus 5? 9. Add up everything in sequence B. What's 2 plus 4 plus 6? 12. Now add those two numbers together. What's 9 plus 12? 21. So no matter which way you do it, you get the same answer. But the important idea is the concept. You can take two sequences that are being added together in a sigma and separate them into two different sigmas. Or you can take two sigmas and combine them into one. Which way you do it kind of depends on what we're trying to do. Yep.
Does the two sigmas have to be like the same?
Yes, the two sigmas have to be the same. They have to start at the same number, and they have to stop at the same number. You could not combine something like this. Say 1 to n, and something that goes like 2 to n. It's like those aren't like terms. Okay, they have to start and stop at the same values. Now, one thing you can do is if you have something that doesn't start and stop at the same value, you can technically fix that. Okay, look at this. Let's just do something real simple. K equals 1 to 3. And let's do the formula 2k plus 1. If you plug 1 in for k, what do you get?
3.
You get 3. If you plug 2 in for k, and if you plug 3 in for k, 7. Everyone agree it's 3 plus 5 plus 7? Okay. Now, watch this. Let's do k equals 0. So I bump that down 1. So I need to bump that down 1. And I need to bump that up 1. So 2k plus 1, so 2k plus 3. Okay. Watch what happens here. Plug in 0. What do you get when you plug in 0? 3. Next number is 1. What do you get when you plug in 1? 5. Next number and last number is 2. What do you get when you plug in 2? 7. So what does that mean about this and this?
3.
They're the same thing. It's two different ways of writing exactly the same thing. What this is called is re-indexing. I changed my index. And I didn't mess up the answer because I changed everything the way I needed to. I bumped this number down 1. I bumped this number down 1. And then I took my k and I put it up 1. So you can change where your index starts and stops if you need to. It's not something we do a lot, but it is something you might see on the test. Like I might give you something like this and say, tell me a formula for adding up all these numbers. And you may come up with this top formula. But in a multiple choice question, I may list the bottom formula. You just have to know that these are really the exact same formula. Yep.
Are they like inversely proportional? So if you went from k1 to k0, that's like -1. So then after that 2k plus 1, like how do they correlate?
So you just have to keep it balanced. So I can start wherever I want. You want me to start at 8? I can start at 8. I just have to look and say, okay, I just bumped the bottom number up by 7, so the top number needs to get bumped up by 7. And this needs to go down by 7. So it would be 2, bring k down 7. So it would be 2k minus 14 plus 1. It'd be 2k minus 13. And now if you check it, plug in 8. What's 2 times 8?
16.
16. What's 16 minus 13?
3.
3. There you go. There's your first number. So that's how you balance it out. So you can write sigma an infinite number of ways. You can start anywhere you want. But I'll tell you 1 is the most common. But sometimes you see 0. I normally wouldn't see 8. That's kind of a random index to start at. But it's certainly correct. All right, so that's how you can take 2 sigmas and break them apart. You can do the same rule with subtraction. If you have 2 sequences you're subtracting, and then you want to add the difference of subtracting the sequences, you can do it on the way on the left, or you can add up all the numbers in the first sequence, add up all the numbers in the second sequence, and then subtract those 2 sums. Okay, and you'll get the same result. So rules 1 and 2 are very similar. Okay, rule 3 is a little different. Rule 3 is if you want to multiply a sequence by a constant, like you want to triple everything in the sequence. All right, let's take sequence A sub k. Let's say I want to double everything in the sequence and then add it up. Okay, 2 ways we can do it. First thing I can do is double each number in the sequence 1 at a time. So let's do it specifically for doubling. It doesn't have to be doubling. I just pick doubling. So let's find 2 times a sub k. If you double every number in that sequence, what do you get?
2, 6,
2, 6, 10. Now, add up everything you just wrote down. So now let's do the sum of all those numbers doubled. What's 2 plus 6 plus 10? 18. Or, we can basically take the 2 and put it in front. So let's just add up all the numbers first. Let's figure out what this is. What's the sum of all the numbers in the original sequence? 1, 3, 5. That gives you 9. And there's a 2 in front to double it. What's 2 times 9? 18. So you get exactly the same thing. Okay, this one's very useful because it allows us to take maybe a sequence that looks complicated, and it's almost like factoring a number out of it, putting it in front, and making what you're adding up a little simpler. So any questions on those 3 rules? All right. So those are all just different properties of summations. All right, so let's try this one. First of all, looking at that problem, can these sigmas be combined together?
Yes.
Yeah, because they start at the same spot, they stop at the same spot. Think of this as like your a sub k, and think of this as your b sub k. So what is happening is you are starting with basically what's on the right, and I want you to put it back together on the left. So take the 2 sequences and add them together and keep the summation exactly the same as it was originally. So where did the summation start originally?
Mick, you asked that again? Sorry.
Where does the summation start in this problem? What's our first index? 1. And where does it stop? N. So when we combine these 2 into 1, it's still going to be 1 to n. But what's going to be in parentheses here? when you combine a sub k and b sub k together? What would your first?
Would it be
6k squared, yep,
And then you got minus 2k,
minus 2k,
and then plus 3.
and then negative 4 plus 7 is plus 3. Perfect. So that uses rule 1. Yep. Any question on how we combine those together? Now again, it still is not fast to do this. If I want you to add up the first 100 terms in this pattern, which is a quadratic pattern, it's still going to take you a long time. Unless you know how to do it, then it won't. All right, what's the next one I got? Okay, so that's the point I've been getting at. So sigma notation, it is a short way of writing things, but it doesn't give you a short way of doing things, okay? Now, this is representing adding up the first 10 integers. It's a very simple formula. Adding up every number from 1 to 10. Now, I can tell you very quickly what every number from 1 to 10 adds up to. It adds up to 10 times 11 divided by 2. It adds up to 55. And to figure out that 1 plus 2 plus 3 all the way up to plus 10 adds up to 55, I didn't sit there and do 1 plus 2 plus 3. I couldn't have done it that fast. All right? So there's a trick I did here. Right? If you wanted me to add up every number from 1 to 100, just going by integers, 1 plus 2 plus 3 plus 4. Well, if you want to add up every number from 100, it's going to be 100 times 101 divided by 2. So whatever this comes out to, 50 times 101, that's what every number from 1 to 100 adds up to. Now, you might be able to come up with some tricks, right? So you don't have to add these up by hand. And if you thought about adding up every number from 1 to 100, all right. Let's see, 96, 97, 98, 99, 100. This might give you a hint at how you could figure out how to add these numbers up. Does anyone see how you could group these numbers to make the calculation of adding up the numbers from 1 to 100 easier? Yeah?
If we're using like what you did before, so like since this is 10, you do 10 times whatever 10 plus 1 divided by 2. I don't know how to describe. So if you were to do for 100, it'd be
I have an idea.
oh, it's just the first 100. There we go. First 10.
Since we have let's add the first number that we have on it with the last number, and then
What does that add up to?
that's going to be 101.
101.
And as we go in further and further, it's going to continue being 101.
Right. In fact, you're going to have 50 copies of 101 added up if you add up every number from 1 to 100. Yep. So what we want to do is, how did I get this though? 100 times 101 divided by 2. Like, where did that come from? Well, that's what I'm going to show you. All right. So what we're going to do is we're going to finish up by looking at some formulas that allow us to get rid of the sigma. So I know I tell you all about this sigma. It's a great short way of writing things. We actually don't want to leave sigma in the final answer if you're really trying to add things up and get a number, like 73. Right? We want a way to evaluate the sigma fast without doing, adding up 100 different numbers. So let's start with this one. This is probably the simplest one to come up with a formula for. Let me show you kind of an example off to the side. C is a constant. Okay, C stands for constant. So let's say I wanted to add up every number, starting at an index of 1, stopping at an index of 4, and that's the formula that's generating the terms in my sequence. 3. It's a constant. There's no variable. So if you take 1 and plug it into this formula, what do you get for your first term?
4?
No.
But you don't, yeah, it's just 3.
Just 3. What if you take 2 and plug it into that formula? 3. What if you take 3 and plug it into that formula? 3. And what if you take 4 and plug it into that formula? 3.
So it's just going to be 3 times 4.
So it ended up being 3 times 4. So what do you think this formula would end up being? C times n. Yep. That's how you can get rid of the sigma if you have to add up a constant over and over. Okay, now that's the simplest one, where you have a constant. Okay, the next one is the one that I was using the formula for to add up the first 100 integers. This is an integer, k. So if you want to add up the first n integers, the formula to do that is n times n plus 1 over 2. Let me show you that it works. Let's pick a number of integers to add up. Not too big, because I want to do it by hand, and then I want to show you how to do it the short way. So let's pick a number of integers we want to add up. The first, how many?
5.
First 5. So 1 plus 2 plus 3 plus 4 plus 5. Okay, adds up to 15. Let's plug in 5 here and see what we get. If you plug in 5, you're going to have 5 times, what's 5 plus 1? 6 over 2. What's 5 times 6 divided by 2? 15, and that's exactly what the first 5 integers added up to. So if you want to add up the first 100 integers, it's 100 times 101 divided by 2. That's where that came from. 100 times 101 divided by 2. Right. So that's the formula for adding up the first n integers. There's also a formula for adding up the first n perfect squares, like this. One squared plus 2 squared plus 3 squared. Let's do that, and then I'll show you the formula that does it quicker. So what's 1 squared? 2 squared? 3 squared? 16. Okay. What's 1 plus 4 plus 9?
13. No. 14.
So 5 plus 9 is 14, plus 16.
30.
30. So if you add up the first 4 perfect squares, you'll get 30. Now, let's look at the formula. N times n plus 1 times 2n plus 1 over 6. I never remember what that is. I'd always have to look that up. But let's plug in 4 and see if we get 30. If you plug 4 into your first factor, what do you get? Just 4. How about the second factor? 5. And the third factor?
9.
2 times 4 is 8, plus 1 is 9. And let's divide by 6. Well, let's see. We could simplify it a little bit. What's 9 times 4? 36. What's 36 divided by 6? 6. And what's 6 times 5? 30. And that's exactly what we got when we added up the first 4 perfect squares. It adds up to 30. Okay, so there's all kinds of formulas you could come up with. I'm not even going to go over the perfect cube one because we're not going to use it. But there is a formula if you want to add up 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed as high as you want to go. It actually looks a little simpler than the perfect square one. But I would say for the test, these would probably be the most important ones that you would need to memorize. And the first one, you can really figure it out. That one's kind of common sense. It's adding up a constant, so that's easier. But the n times n plus 1 over 2, you would want to know that one. Okay, don't worry as much about squared and cubed. Okay? All right, so let's try, let me see what we have left. Not much. Okay. So let's try this one. I want to find a formula to add up the first n terms in the sequence, in the series, negative 2k plus 3. And let's pretend n was a big number, 25,000. I don't want to have to plug in 1 through 25,000, figure out what all those numbers are, and then add them all up. Okay, that's going to be an awful lot of work. So what we need to do is take this sigma and break it down until we get things that look like one of these first two. Okay, we need to get it simpler. Once we break it down and it looks simpler, then we can substitute in these formulas on the right-hand side. Okay. So the first thing I want to do is break this up into two sigmas. There's one. There's two. What's going to be the starting index of each sigma? K equals 1. What's going to be the stopping point for each sigma? N. And I don't know if it's technically called this, but I call it, it's like my argument. It's like my formula. What's going to be the argument? It's going to be a negative 2k. And what about the argument to my second sigma? 3. Now this one is good. We have something we can go look up for that. We're adding up the number 3 n times. So we can figure out what that equals in a second. Now, the second part almost looks like this one. There's only one thing that we don't want here. We don't want the negative what?
Negative 2.
Yeah, we don't want that negative 2. But if we go back,
On the other side?
yeah, if you have a number in front of a sequence, you can take that number and put it in the front. So let's do that. Okay. So put the negative 2 in the front. Now we have from k equals 1 to n of k plus the sum from k equals 1 to n of 3. Now what I want to do is basically substitution. I want to look at what I have here. I'll bring these other formulas back up. Just focus on the ones you need to. And let's start with this first one. What can you substitute in for what I just circled?
N times n plus 1 over 2.
Yeah. This evaluates to the formula n times n plus 1 over 2. Okay, so we gotta clean that up a little bit. And what does that evaluate to?
3n.
Yeah, it evaluates to the number here times the number there. That's the pattern, 3n. So now we just want to combine like terms, and that's the answer. All right. So distribute this out. So it's n squared plus n over 2 plus 3n. And how would I write this part as two separate fractions?
n squared over 2 plus 2 over n.
Yep, so I'm just going to think of it as 1/2 n squared plus 1/2 n plus 3n. So that's going to be 1/2 n squared plus, what's 1/2 n plus 3n? 3.5 n or 7 halves. Yep, I'm just going to think of it like that. So now what you just figured out is a formula for adding up the first n terms. So if you wanted to take and add up every term from 1 to 25,000, in this formula. All you have to do now is plug the number 25,000 in for n, and you'll have your answer. Very, very
So did the
simple.
-2 just like disappear pretty much?
That's what I was gonna ask.
Oh, did I not copy that? Oh. Sorry. I should have copied that there. And I should have copied that. Yeah, that should have stayed in front. So, what would happen now, because we have that, let me fix it from this step down. Because we have a -2 in front and we have a +2 in the bottom, what's going to happen to the 2's? Yeah. The 2's are actually going to cancel. So I made a mistake and didn't copy that down. So now, all that's left is the negative. So you have -n squared, and then -n times +1. So because the 2 cancel, it's actually a simpler formula than I had. Thank you for pointing that out. And what do we get for a final answer?
N squared plus 12.
Plus 2n. Yep. So now, if you wanted to add up every number from 1 to 20,000, all you have to do is plug the number 20,000 in for n, and you get your answer. Yeah, so if you do have that number in front, make sure you copy that down. That goes with it. So I'm not going to even scroll. That's the final answer. All right, any question on that? Now, I could give you a sigma that ends up with a k squared or a k cubed, but I'm going to stick to formulas right here that are pretty much like linear. They're not going to have squareds or cubes. Okay, they could have constants, and they could have to the first power, but that would be it. I would adjust that one. I would probably give you something like this. And it's very, very similar to the last one we just did. Any questions on how you would do one like that? You just split it up into the 2, and then you're going to take the 5 and put it in front. And that's pretty much it. Okay, so last question, last formula. So those patterns I showed you, I showed you 4 patterns. We're using 2 of them. You now know how to add up a constant over and over, and what the formula is for it. And you now know how to add up integers from 1 up to as high as you want to go, and that's the formula for it right there. But what if we wanted to add up on terms like this? Let's say we had 4, 8, 16, 32, 64, and so on. But are we adding up the same number over and over?
No.
No, then it doesn't fit. It doesn't fit this rule. Are we adding up the first n integers? 1 plus 2 plus 3 plus 4 plus 5?
No.
No. Then it doesn't fit this rule. It's neither one of them. Those are the only 2 shortcuts I've shown you for adding up numbers. What is happening here? Yeah?
It's doubling.
It's doubling. And what kind of sequence is that if it multiplies by a number each time?
Geometric.
It's geometric. So if you want to add up the first n terms in a geometric pattern, that's the formula for doing. Right? And maybe I'll use the example I just wrote down. Let's add all those up. So this is a shortcut for adding up the first n terms if you have a geometric pattern. So now it just gives you one more thing you can look for. You can add up constants, you can add up integers, now you can add up numbers that fit a geometric pattern. let's do it by hand. And I'll be honest, if I was just adding those numbers up, I would just add them up by hand. But let's say this list went on for another 40,000 numbers. Well, I'm not adding that up by hand. Okay. All right, so let's add them up. 4 plus 8 plus 16 plus 32, 64, 128, and 256. All right, so that adds up to 508. Now, let's try the formula and see what we get. How many terms did I just add up? Okay. How many? 7. So we're going to find the 7th partial sum. What was the first term in that sequence?
4.
4. And what did I multiply by each time? What was my R
2.
value? My R value was 2. And how many terms am I adding up?
7.
7. And what was my R value again?
2.
2. Let's do that out and see if we get 508. All right, so we have 1 minus 2 to the 7th. That's negative 127. Let's see, so 4 times negative 127. What's 1 minus, I'm sorry, what's 1, yeah, 1 minus 2?
Negative 1.
Negative 1. All right. What's negative 127 divided by negative 1? 27. And what do you think 4 times 127 is going to be? It's probably going to be 500. There you go. So that gives you a quick way to add up as many numbers as you want in a geometric sequence. You just have to know 3 things. What's the first term? What are you multiplying by each time? And how many terms do you want to add up? Now, if you're not multiplying by the same number each time, then it's not a geometric sequence. You can't use this formula. All right. Any question on that formula?
I probably wasn't here for it, but do you have like a series formula for something like that?
Well, there'd be you could generate a sequence formula for it.
Yeah.
That's what we did yesterday.
Okay.
Yeah. But this is the formula for this series. Okay, so big difference between yesterday and today. Yesterday, you were just finding numbers in a sequence, putting commas between them. Today, you're taking out all those commas and putting in plus signs. And you're adding them all up. Okay, and I've shown you a few shortcuts for doing that. Constants, integers, and geometric numbers. If you've got something other than one of those 3 patterns, unless you're pretty clever and you figure out a shortcut, you'd have to do it by hand. Okay, but there always has to be some kind of shortcut, as long as your pattern is predictable. Okay.
Are you gonna look at like exponential growth for like this unit all, because like that's another kind of sequence thing? Is that just like keeps on growing?
That's geometric.
Geometric. Oh,
That's what we looked at. Yeah.
but you said addition. How's addition exponential?
That's arithmetic.
Arithmetic. What would an exponential one look like?
It would be geometric. Anything geometric is exponential.
Oh, so like when multiplied by 2 each time,
Yep.
it's technically exponential growth.
Yep.
Okay. Yeah, that comes.
So let me double check. I need to adjust that a little bit. So 1 through 6 is okay. Let me just adjust that. I'm going to do 1 through 8. And then we're going to do 13 through 19. Okay, so 1 through 8 and 13 through 19. Alright, so we'll take a look at that tomorrow. And tomorrow we're going to do an infinite series. And it might seem like that would be harder to add up infinitely many numbers rather than a finite amount. But actually, some of the formulas are easier for infinite than they are for finite. Okay, and we'll look at that tomorrow.